Okay, let's go for trying to get these. These are, I think, are a little bit more difficult because they actually require you to remember the exact polyatomic ion, okay? So everybody knows the first part of this one. Go for it. Okay. K. I'm going to put K1 plus to remind us it's ionic. And then what's dichromate? Cr2O7. Remember, chromate is CrO4 2 minus. Dichromate, Cr2O7 2 minus. So that's dichromate. That's a big, huge polyatomic ion. And you can remember, Cro is like chromium. That's why it's got Cr. 8s have, oxygens, but you got to remember it's 7 oxygens in this case. And then the whole dichromate thing is just saying I have 2 chromiums. So that's dichromate, 2 minus charge. So what do you get when we put it together? K, 2, parentheses, Cr2O7. And you don't have to put the parentheses, but I'm leaving it to show it's potassium dichromate. It's got a long last name. Next one, ionic or covalent, first of all? Ionic. Why ionic off the bat? Cobalt's a metal. Right. And you can see it's telling me a charge, right? So that charge is of cobalt. So cobalt, 3 plus, oxygen, charge. You probably had to look at your periodic table for that. 2 minus, crisscross, what do you get? C little o, 2, O, 3. There you go. Just emphasize CO and then O. Okay, next one, ionic or covalent? Ionic, because calcium is a metal, right? If you start with a metal, you are definitely ionic. So that's calcium, charge of calcium. You don't have to know it. Look on the periodic table for it.
2 plus.
It's a 2 plus because it's in the group 2. It loses 2 valence electrons. Nitrite. Okay, so first off, you see ite, and you're like, not straight from the periodic table. Do you remember nitrate? NO3. You remember nitrate maybe as NO3 1 minus. So then what's nitrite? NO2 1 minus. So you just drop an O. So if you know the 8s, so when people are like, do we have to have these memorized? If you can memorize the 8s, the rest of them kind of come because the ites drop it down one oxygen. So then we crisscross. What do you guys get? 2. Good. Okay. So it's intimidating right now, but you just got to keep working at it so you can keep looking at it every day. Potassium permanganate. Potassium, okay, first of all, ionic or covalent? Ionic, because potassium is a metal. Most of the periodic table is a metal. Anytime it's an ionic one, you got to make sure you get your charges. So that's potassium 1 plus because it's in group 1. Permanganate. Good. So here's, it's not great, but you see manganese kind of in there. Manganate is manganese, that's Mn. And the 8 means that you've got an oxygen. Per usually means a plus 1 oxygen. So it's actually got a lot of oxygens. 4 in that case is our permanganate. That per does not tell you 4. There's no correlation, but just think more oxygens than normal. And charge? 1 minus. Okay, so potassium permanganate is K1 MnO4 1. And I'm going to keep my parentheses there for you. Hydro. What is this telling us? It's a binary acid. Good. So it's just H plus with what? With P, but what's P's charge? What's phosphorus's charge? How do you know 3? Okay, so it's on periodic table, 5th group over, 3 electrons more would make it octet, so that's why it's going to have 3 negative charge. Crisscross, what do you get? H3P. I saw a lot of HPs, right? The thing that you have to remember about acids is they act ionically, meaning that they need to have charges so you can crisscross them. Okay? Who got a 70 or higher? Feels like they got 70% or higher. About all 11 of them. Okay, we need to practice. All right, I will take prompts at 9 questions now, but I'm going to take prompts at 9. I'm going to literally check every single one to give you feedback, because this is one of the most important parts that we talk about. Questions on prompts at 9? Yeah. You're going to have to tell me what it says. I can do it from what it says if you can do that for me. Somebody else have another question right now? Yeah.
There was one that was like COXO4
Okay, so this was the one I went over with a couple people yesterday. This has this one has a longer name than normal. Okay, so I think you can name the first name and the second name. Can you do that for me, everybody? Cobalt what? Cobalt, I heard cobalt sulfate, but cobalt is a transition metal. So what's its charge according? What's sulfate's charge? SO4. Sulfate. 2 minus, right? Sulfate is a 2 minus. So what is it? It looks like cobalt and sulfate have the same charge because they reduce down. So what's cobalt's charge? 2. Okay, so cobalt 2, sulfate. Then you name this part, and this part is called a hydrate. Why does that make sense for it to be called a hydrate? It's hydrated with water. Okay, so the hydrate word is just say the name of the number with a prefix and then say hydrate. So then you'd say hexahydrate. And you're going to have a lab with this soon. But we actually had one of our very first labs. We used this blue solid and you ground it up in lab 1. And that was called copper 2 sulfate pentahydrate. How many waters did it have if I said pentahydrate? 5 waters. And you dehydrated it, went from blue to white. So we've kind of actually seen that, but I didn't expect you to remember it. I knew I was going to go over that one. Yes, ma'am.
So number 7, a subscript in a chemical formula is used to indicate the number of atoms of a given element in the smallest representative
Is that a true false? That is always, well, yes, that is always true, because its subscript is going to be indicative of the number of atoms it requires of that element, and it is the smallest because we always reduce it. Specifically ionically reduced, covalent we do not reduce, but that's still the same. That still is always true, because covalence we don't reduce, but that's still representing the number of atoms in their molecule. Okay, more from prompts at 9 that you know you gotta ask. No more? Yeah.
The acid ones, when it's like BMBI or 2.
You can just put acid there, or you could put binary acid like that. You can call it binary ionic because it acts ionic, but acids are actually molecular, so if you put BM, I'm fine. If you can put anything, I'm fine. Acids, that's fine, because they're kind of their own separate category. Yeah.
What is bromate?
Bromate, good question. Okay, so on your polyatomic ion list, you guys tell me chlorate. Chlorate, ClO. 3 charge. 1 minus. Tell me iodate. Is iodate on there?
I don't think so.
Okay. I want you to look at the periodic table. Tell me what the halogens are. Periodic table. Chlorine, bromine, iodine. I'm stopping there, okay? Those 3, chlorate, bromate, and iodate, they are all exactly the same. It's just their halogen is different. So chlorate, bromate, and iodate. So you can actually easily get it from chlorate. So I think it was sodium bromate, I think, on that particular problem. Barium bromate. Barbara. Oops, dude. There you go. Barium bromate. Crisscross your charge. Another one on prompts at 9 right now. I will give you feedback as soon as I can. Yeah. Sarah.
Sodium bisulfate.
Sodium bisulfate. So sodium is a metal, so it gets a charge. bisulfate. Sulfate is SO4 2 minus. Bisulfate means it has an H plus in the front, so that H plus counters one of the charges, negative charges, so it's just SO4 1 minus. Crisscross that, you get NaH SO4. Okay, how about reading guide 7? Reading guide 7 was all based off ionic stuff, right? Ionic, ionic, ionic. So what do you think we're going to talk about today? Ionic bonding. And then we're actually going to talk a little bit about covalent bonding, okay? So, yes, ma'am.
I have a question about reading guide 7.
Can you ask the question? Tell me the full question.
It was just a question. What's the difference between a chemical formula and a covalent unit?
Okay, the chemical formula is kind of like an umbrella term that says anything, ionic, covalent, acid, organic formulas, anything is just the chemical formula. Specifically, when you say formula unit, it's the chemical formula of an ionic substance. If I said molecular formula, that's the formula of a covalent substance, and so forth. It's just getting more narrow. Okay? Okay, if you're good with that, pass up reading guide 9 and problem set 9 and reading guide 7. If I already got your reading guide 7s, I have it noted in my book. Okay? If you need a stapler, just dog ear it, mouse staple it. I have very few. I don't know if this one has staples. I have some staples here. Okay, so we're gonna move to bonding today. Pull out your foldable so you guys can draw some of these things on your foldable and note a couple more properties on your foldable. It's okay if you don't staple. I will staple. Those are the last people come up with staple. Just pass them up for me. Today is an Enlo Talks more today than normal, so I'll give you guys a break. No worries. Yeah, let me get that for you. Hi, we have these on right now. Markers have diminished because people don't put them up, so today let's just probably put them up. Some people have specific color preferences. You can put some of it on your foldable, and I'll tell you specifically what. Okay. Otherwise, just on this. Okay. Let's go ahead and get settled, like in the next 20 seconds, so that we can start. The warm-up took a lot longer, so I'm going to ask us we're going to try to get through covalent bonding types today, because we have a lab tomorrow, Thursday, and Friday. Okay, tomorrow's lab, we are, so just FYI, tomorrow's lab, I need you to bring me a penny. Okay, a penny. Just one. You can either bring me a pre-1983 penny or a post, or if you just want to bring both, that's totally fine. Okay, so tomorrow, right on your hand and your arm someplace, bring Enlo a penny. And I will give it back to you, but in better condition. Just a pre or post 1983 penny. Look at the year on it. Okay, so that's just a side note. Write that down. Okay, so here we go. We need to talk about bonding. So far we've talked about nomenclature. We know how to name a lot of stuff. We know a lot about bonding, but now we're going to start drawing the bonds. So drawing the bonds requires one to know about why in the heck are these things bonding. The main purpose, and the stuff in red or highlighted in yellow, is really the most important piece of information. So if that's all you write, that's all you write. That's totally fine. So whenever things come together to bond, it's because they're happier together than they were apart. When I say happier can mean two things. With me, everybody? Yeah? We're looking around for markers? No. Okay. This does not have to be on your foldable. This can be on normal paper if that's what you're looking for. I'll tell you specifically what should be on your foldable soon. Bonding is going to be coming together because whenever they are together, they're happier. And everything is happier when you're in a chill state, right? If you're like high and anxious and stressed out, that's really high energy. You're just like freaking out. That's not happy. Okay, we have a process of bonding because the two atoms together have lower energy than they did separate. And so it's like this Goldilocks region in the middle where they like to be together. So that's why we form ionic and covalent bonds. And the happiness index is related back to how many valence electrons they have. So those two things are directly related. If you have 8 valence electrons, that means that you are happy. You either do that by, and that's down here at the bottom, you can either do that by donating electrons to get a full octet in your outer valence shell. You can either share electrons to get that, and that's really about it. That's why we have two types of bonds that we generally talk about, ionic and covalent. And this other stuff in the middle is a lot of detail about the energy component here that we're talking about. So the particles, the two atoms, they come together, and as they come together, they take that potential energy that might be really high, which is very unstable, and when they bond together, they come down to a lower potential energy state, which makes them more stable. And basically, this is going back to something called Coulomb's law, where the protons of the nucleus are attracted to the electrons here, and the proton of this nucleus is attracted to the electrons here, so they form an attraction for one another. So that's kind of what that's referring to as the attractive components of the nuclei. You don't have to write all that down, but just the red and the highlight there. So octet rule means what again? 8 valence electrons. That's it. That's what we gain or lose according to our number of valence electrons. I'll give you guys another second there. And soon we'll be playing with our little chemistry Legos sets, okay, to start to show how the bonds occur. Yeah.
So it forms by like being added to.
Yeah. So if I have 7 valence electrons, somebody can give me an electron, and that gives me 8 valence electrons. But also now I have an overall negative charge, like chlorine or something. Okay. So these are properties you already have in your foldable for ionic. Yes. Let's just look here. We know they transfer electrons to make the bonds happen. We know they make ions. That says electrostatic force. It's overlapping, but electrostatic force. Electrostatic just means opposites attract. So if you wanted to add something like that attractive force is in the middle. They are holding them together. We know they have crystalline structures. We know they're very strong. This is highlighted part is a new part that I've added here. So if you would like to add at the bottom of your ionic properties, their strength of their attractiveness, it depends on their charge product. And I'll give you an example. So first of all, it says depends on lattice energy. What is a lattice again? It's kind of like a box. That's how the structure looks, and I'll show you a picture. Here's what a lattice looks like. I'll go right back to that slide. Here's a lattice where the ions repeat itself and layer by layer by layer by layer. So if you're wondering what that is, there you go. But the strength of the ionic attraction is dependent on their charge product. So when I say charge, what are you thinking? You're thinking positive or negative, like 1 plus, 1 minus, stuff like that. When I say product in math class, what do you think?
The multiplication.
Multiplied charges, okay? Not product in chemistry, like yield products, okay? I'm talking about sodium's plus 1 charge and chlorine's 1 minus charge. What's the product of that? 1, okay? I'm just going with simply a magnitude, not a number here. So that's the charge product of sodium and chloride. Versus magnesium chloride. What's magnesium's charge? I hear it, yeah? What is it? 2 plus, and chlorine, so chloride, negative 1 again. So what's their charge product? 2. So who has a stronger bond? Magnesium chloride. That's all this charge product thing is. So magnesium chloride had a 2 plus and a 1 minus charge, and the other one was sodium chloride, which has a 1 plus and a 1 minus. They multiply together. The stronger bond is magnesium chloride. That's all you have to do. Figure out which is the stronger ionic bond. You okay there?
So the positive and negative does not matter.
Yeah, we're just looking at magnitude. Yep, just looking at magnitude. Good point. So that's why I just did like absolute value. Okay, so then we have to talk a little bit more about covalent. And the stuff that we haven't talked about are the ones with the hearts or the highlights here. So we know that they share electrons to make a bond. We know they have a molecular shape. I think previously we just said molecule. And now we're like, okay, molecules look like what? That's what we're going to start getting into. They have a shape, and they actually look kind of like this, or like this. They have funky shapes. A lattice is simple. A lattice doesn't change. A lattice is a box, is a block. That's why we don't have a lot of confusion about what does a lattice structure look like. But molecules come in many shapes and varieties. So that's what we're going to be using today in a couple of days for our labs to build them. So when I say shape, the shape is based off of this VSEPR theory. And this is something you'll define in chapter 8 in your reading guide, and I'm going to define it today too, but just put VESPER. VE, or valence shell electron pair repulsion. Valence shell electron pair repulsion theory is what that stands for. Valence shell electron pair repulsion. And that's like in a couple slides as well. So that's how their shape is determined based on these valence shells of electrons and how do they bond together. And then the energy of that is based on their shape. But what you really need to know is that all covalent bonds are weaker than ionic bonds. So there's a hierarchy. Covalents are weaker. Yeah.
You said VESPER stands for what?
Valence shell. I'll write it down. Valence shell electron pair repulsion theory. We just call it VESPER, even though it's not how you say it. The other properties we've already noted, so that's why I like the bowl, because now everything's kind of coming back together. Yeah?
Why are covalent bonds weaker than ionic bonds?
Because ionic attraction, so like that positive and negative opposites attract, that's like a field, an electrical static field of attraction. And covalents don't have that kind of attraction. They're just kind of like, hey, these electrons are going to hang out between us. If we break apart, we kind of break apart. There's not an opposite attraction, a magnetic field attraction. Okay, so we already went, that's what the lattice structure looks like. We did that. These right here, have you seen these dot structures before from middle school? Some of us are going to, yeah, some of us are saying no. Okay, so these are Lewis dot structures. That is just what they're called. Lewis is the guy who came up with it. They have dots, and now we call them structures. It's pretty simple. What do you notice by group by group by group by group? How many dots they have? How many what? How many is based on the number of the group? What does that also determine? The number of valence electrons, right? So Lewis dots are surrounded with VE, number of valence electrons. That's all they are. So we're going to draw some ionic ones, which are really simple, and then draw some covalent ones, which are a little bit more complex, because then we have to start showing them being shared versus donated. And this is kind of the fun part, too, through a lot of drawing. So all the group 1s have 1 dot. All the group 2s have 2 dots. All the group 3s have 3 dots. All the group 7s have 7 dots. And that relates back to why do we share, why do we donate? Because everybody wants to meet octet, which is the 8th group. The only one that's weird is helium. Helium is so itty-bitty, it cannot even hold 8 electrons. It only gets 2. It's just small. There's one exception. We good here? Give me some feedback, people. Yeah? Thank you. Okay, so these, you're going to have 2 kind of big slides. This is the instructions for how to draw ionic bonds in a Lewis dot model. Then we're going to have another one later on for covalent. This is probably the most important slide with example. If you want to take a picture of it, it's on video. It's also, you can write it down. And this, if you have room on your foldable book, that's fine. If you don't, put it on another paper. So we're going to practice drawing some of these. And I think the example kind of explains the process. Basically, you draw the exact Lewis dot structure of each element. So sodium is in group 1. It gets 1 dot. Chlorine's in group 7. It gets 7 dots. And then your job is to decide, is it easier for sodium to lose or gain and chlorine to lose or gain? Because we know they're going to form an ionic bond. How do you know that right off the top of your head they're going to form an ionic bond? Okay, well, because we can donate easily, and because one is a nonmetal and one is a metal. So sodium being the metal is generally going to lose electrons. That's just the rule. Metals usually have low numbers of electrons, so they lose. So then I'm going to draw that happening. Here you go, chlorine, my friend. Now you owe me. I want that positive charge. You take the negative charge. So you're showing the electron being donated. And then in the end, sodium, which has no electrons, now has a 1+ charge. And chlorine, which was the nonmetal, which generally is going to be gaining electrons, now has an extra electron, so it gets a -1 charge. There you go. The brackets surrounding that just say, these are mine. That's basically it. The chlorine has all 8 electrons now. Overall, though, 1+ and 1- negate each other, and that's why everything ionically is always going to be neutral in the end, because they counteract each other. You good with that example? Some of you are still writing? That's what the structure kind of walks through too. And then I'll leave that right there. As you're considering this, think about your electronegativity series. Which hand was that? Right hand or left hand? Left hand, because right hand was radius. Okay, so right hand was radius, Left hand was electronegativity, amongst other things. What was the definition of electronegativity again? Yeah. Perfect. It's desire for, or I'm going to say pull, because desire is more like electron affinity. Pull on electrons in a covalent bond, okay? So specifically, I'm going to stick with covalent for this one. Or ionic, really. So let's just go bond. I won't limit us here. So if you have a really, really, really strong pull on your electrons, you're going to take somebody else's electron, right? So why does that make sense for sodium versus chlorine? Who has the higher electronegativity? Chlorine, by far, right? It's like sodium's way over here, chlorine's way up here. It's not only farthest to the right, it's also farthest up. Sodium's just got, farthest up, it's very close to the left. So that's why chlorine wins, that's why it actually gets the electron. So this relates back to our trends. All right, let's do one for magnesium oxide. So magnesium, 2 dots, why? Okay, it's in group 2, it's got 2 valence electrons, plus oxygen with what? 6? 1, 2, 3, 4, 5, 6. I'm not real specific on where you put them, as long as they're generally around the atom. And then do what with it? Donate what? Magnesiums to oxygen, okay? And then do what? So magnesium has a what charge? 2, because it lost 2 electrons, and oxygen has
8
so octet, it's got 8 dots around it, and 2 negative charge. But why do those 2 pluses and 2 negatives not appear here?
Because they cancel.
Right, they reduce down to 1, so it's magnesium oxide 1, 1 versus 2 and 2. Okay, so I'm going to keep saying magnesium oxide. I want you to think the same thing and don't just go MgO. Think about your nomenclature as we're going through these. Yeah.
Why is there 2
Because it gained 2 negative charges. It gained 2 electrons.
Oh,
Okay? All right, so ionic is very simple. I don't think there's much more to explain about that. Looking at this, the way that this has formed, what kind of bond is this? How do you know that? You should know it 2 ways. What's coming together? 2 nonmetals. Boom, you're like, that's covalent. And then what do you see? Shared. You don't see any, you see a shared space in the middle with 2 electrons, and you don't see any charges. So that's kind of how the Lewis dot models are going to look for covalent bonds, okay? Between these, which is more electronegative? They're the same. So does somebody pull more on the other?
No.
No. So they're sharing them equally or unequally?
Equal.
They're sharing them equally. Okay, so that's something called, so shared equally is something called a non-polar covalent bond. Non-polar covalent bond. So if I'm saying they're shared equally, and then I'm saying that's called non-polar, how does that relate? What does polar mean then? So polar bonds are what? What do you think? I'm going to say polar covalent bonds to keep us away from saying ionic. Give me something.
One atom pulls more on the electrons than another one does.
Perfect. So unequal sharing. So there's a difference. This one's unequal sharing, if you say polar covalent bonds. And then shared equal sharing is non-polar covalent bonds. And I'm going to show you some examples of both. So polar means opposite ends, so one side is pulling harder than the other, meaning one is way more electronegative than the other. This one's sharing equally in this case because both of them have equal electronegativities. They share equally. Neither side has more electrons than the other. How does that change for HCl? And I don't expect you to memorize electronegativities numbers. I expect you to memorize the trend in general, up and to the right. I have a little chart for you guys to use in class, and I'll show you where it is on our website too. You're using this at home, the electronegativities. We're actually going to give them numbers today. We will use this a lot for the next 3 or 4 days, so make sure that you guys know how to read this. There should be an extra one coming up. Okay, so HCl. Tell me the difference electronegativity numbers for H and Cl. Who's ever got their little chart? Tell me what the number is under H. 2.2. All right, so for chlorine, 3.1. You guys see those numbers on there? H, you need an extra in your math class one. Okay, so 2.2 and 8, oopsies, and 3.1. What's the difference between them? What's the, like, mathematical difference? Don't tell me, just do absolute value. 0.9? 0.9. Looking at the top, you mean, okay, pass the one back, sorry. Looking at the top, what's the, what category does that fall in?
Polar.
Polar what? Polar covalent. Okay, so this bond between H and Cl, I'm going to draw it just like as a line instead of 2 dots. That line indicates that chlorine is more electronegative, and that's the 3.1. H is less electronegative. And I don't know, but don't you see this side over here kind of looks like a plus? If you draw it, because it's this right here. That's the arrow that I'm drawing. It's got like a hash mark on one side and an arrow on the other side. If you look at it, it kind of looks like a plus. So does it make sense that more electronegative, that one steals the electrons more, right? It pulls it to that side. This has a slightly negative charge. This right here means partial, it's a sigma delta, sigma negative. That means slightly negative. I hope you're drawing this, because this is something very important, okay? This is a covalent bond, and we're going to draw it probably 2 or 3 different ways. So we had our H and our Cl. We saw there was a difference in their electronegativities. One was a 2.2, one was a 3.1. Then we said, okay, well, on the chart, what does that tell us? It tells it's polar covalent. Polar covalent, did that mean equal sharing or unequal sharing? Unequal sharing. Unequal sharing of electrons means that one side is more negative than the other side. Not full-on positives and negatives, because that would be in the ionic category. But this side over here, chlorine, has a bigger number in terms of its like electronegativity. So it's hoarding the electrons on this side just a little bit more, which makes it have a partial negative charge. Not full negative, but partial negative. So what do you think that leaves H with? A partial positive charge. Okay, so what I drew above that, this little hash mark arrow thing, that actually has a name. It's called a dipole moment. That's just the name of the arrow. It's called a dipole moment. And we're going to draw those today quite a few times. So this kind of is a big picture, and then we're going to kind of go back through baby steps. Dipole moment points towards the more electronegative one to say those are where the electrons are really existing. And the side with the hash mark, which kind of looks like a positive, indicates the more positive side of the bond. Yeah.
Partially negative and partially positive meaning.
It just means that that side of this bond, so there are 2 electrons in this bond, okay? Equal sharing would be one side and one side have equal of numbers of electrons, and so neither of them is more negative or more positive. They're equally negative positive. Equally negative, let's say just equally negative, because those are negative charges. If the electrons, instead of being right smack dab in the middle, hang out closer to chlorine, because it's more electronegative, it's still bound together, but they're closer that way. It means that chlorine takes on this slightly negative charge because there's more electrons hanging around it. And then there's less electrons hanging around hydrogen, so it takes on a more positive nature. Slightly positive, yeah.
Does the arrow always be to the right?
Always towards the more electronegative one. This one, 3.1, is more electronegative than 2.2. It's always towards the more electronegative one. So you draw it based on where the more electronegative one is. I could have drawn it CLH and it was an opposite. Yeah.
So what would more electronegative?
Right? Because it's more electronegative, so it takes on the negative charge. Okay, there are many more examples here, okay? This is a big picture. We actually talked about a lot of stuff right here. So if you feel a little confused, I'm going to clarify some of that. Okay, this actually we kind of just went through. Write down what you mean. I'm going to explain it kind of just one more time for us, and then we'll take a quick break. Bonds come in 3 varieties. Ionic, okay, 2 varieties. Ionic and covalent. But the covalent part can either be shared equally or unequally. And that's what this and this are referring to. Dipole moment again. What does that look like? The arrow with the little plus mark on the side. That's what the dipole moment is. So if you're a notes person, you're like, I need to have exactly what she said. This is kind of exactly what I just walked through. And then I'm not going to leave this up here forever, because we did just talk about it. And I'm going to give us a couple of examples embedded within this so that we don't have to do a ton of examples later. So the nonpolar covalent, maybe you guys with the electronegativity sheet, you guys look there and you tell me where you can give me two atoms that go together that would have zero difference in their, very little difference in their electronegativity. Our first example we did was chlorine and chlorine. So that's why this bond here in the middle is just a nonpolar covalent bond, because they're equally shared. Tell me one similar to that.
Two are the same or one?
You can tell me one that's the same or ones that have very little differences in their electronegativity.
Platinum and iridium.
Okay, hold up. We're talking covalent, right? So remember, covalents are still non-metal, non-metal. We don't change the rules of covalent bonds. Platinum is a metal. So think upper right corner. There's not many, right? What are you saying? You're saying phosphorus and... I saw silicon and phosphorus. What else? Arsenic and phosphorus.
Sulfur and selenium.
Sulfur and selenium, yeah. Okay, so all of these that are bound together, I'm drawing just a single bond between them right here. Those numbers, I could write them down, but you guys can see them here. They're all less than 0.4 differences in their electronegativity. So what I want to draw are, on this one, I can't draw any dipole moments because none of them have a polar covalent bond. So let's go through and let's look at maybe carbon and oxygen. Carbon and oxygen, what are their numbers? 2.5 and 3.4. That difference is 0.9 again, right? 0.9, polar covalent. So that's how I write it over here for myself. And then which side is more electronegative? Oxygen. So you draw the arrow above it, pointing towards oxygen. There you go. That's it. And I'm drawing all of these things, these like lines that I'm drawing. How many electrons is that representing? So when I draw a line like this, 2 electrons, because they have to share 2 electrons. One puts one of them in the bond, the other one puts the other one in the bond, and now they share 2 together. So line means 2 electrons. Questions so far? They can't share one. They have to, it's a mutual relationship. Like I scratch your back, you scratch mine, I put 1 electron in, you put 1 electron in, but then we pretend to share them both. Okay, and ionic bonds are going to be things like, yes ma'am?
Does it have to be 2 electrons for the line?
The line, 1 line means 2 electrons. That's a standard protocol across all international chemistry. 2 lines, though, good question. If I drew like this and this, that would be a double bond. Yep, and that would be 4 electrons, and we will get there. We will make them share multiple times. Ionic is just simply like, for example, sodium and oxygen. What's the number on sodium on here? 0.9, and oxygen was a 3.4. Huge difference. What, like 2.5 difference? So I'm not even drawing a line. I'm saying 2.5 difference is ionic, and then I actually am going to go through and just put their charges on there for myself to remind myself it's not sharing. It's like, hey, I donated electrons. And that's not this like chemical formula. It's Na2O anyway, sodium oxide. Okay, and this is just a picture to indicate all of this to you once again. So covalent, you see that this big shape here is just an electron cloud. Does the electron cloud look equal on both sides?
Yes.
Yes. So ionic, so nonpolar covalent. Once it starts morphing into one side being bigger than the other, that means that the electrons are moving that way. So this side over here has a bigger amount of electrons. This side here has less electrons. So I can draw these a little bit better. This is partially negative, and that's partially positive. And then this one's like, hey, we've totally separated our clouds. We're not even like bound together. We're just electrostatically attracted because of the negative, like full negative and full positive charge it has. Okay, before we do more, get up and go see somebody. You guys need a break, okay? Go high five somebody. Talk about what we just talked about.
Splash some water on your face right now.
Here's the take some of Today's Tuesday. I don't know, it's Tuesdays.
Okay, so if we show you the videos tomorrow,
Yeah. Oh, no worries about it.
okay.
We'll get it back.
I know. Where'd Josh go? Darn, he's still taking his test. I was going to ask him about the polyatomic ion, like, memorization.
Josh, do you have a good way to remember the atomic ions? You just memorize them. Just memorize them. All right, guys, go back to your seats for me. I think that was a good enough break for now. We need to get to drawing.
Enlo, do you have teal pens?
Today I have meetings on Tuesdays. Tuesdays are no good for Enlo except for after school. But I do have teal Wednesday and open months on Thursday and then teal on Friday. Okay, quick note, look up here. I don't know if you guys noticed on your little sheet. This is one of the old sheets right here. The noble gases over here, yeah, helium, neon, and argon, they don't have numbers. Meaning what about their electronegativity? They don't want any. Please do not share electrons with me. I don't want your electrons, and you're not getting mine. Peace, right? But these other ones, krypton, xenon, and radon, they're like, I mean, I got a lot of space. I'm a pretty big element, atom. They're large down here. I got room. I got extra electrons, and they're willing to bond, okay? So a lot of times we say noble gases are too cool to bond, right? But that's the upper ones. They're snotty. But the other ones they're kind of cooler, more down to earth, and they will bond. Yeah.
Some of the ones on the bottom on our sheet don't have numbers. Is that because they're not known yet? Or?
Yes. That's because this is an old periodic table anyhow. There are more things in it. We usually will not bother with those though. We stick to generally easy ones. Okay. So here, I know this looks long. Let me walk you through an example first. This is this is how you draw covalent structures with Lewis dot models. And this looks like a lot of steps, but in your head you're doing them pretty much in order, I think, by yourself. So let me just start with an example, and then I'll go back and we'll point through those. So do this example with me. I don't think you're going to have room on your proposal for this. This is going to be what we talk about together. Okay? Write it down. This is called ammonia, by the way. Ammonia looks like ammonium. The ammonium has an H4+. All right, so ammonia has combined consists of 1 nitrogen atom and 3 hydrogen atoms. Everybody comes to the party with electrons. How many electrons, valence electrons, does nitrogen bring to the party? No, it looks like it. Look at your periodic tables. You guys can use your periodic tables. Look at that. Tell me what the valence number of nitrogen is, because it's in the 5th group, right? So first step, count valence electrons in the party. That means the whole shebang. So nitrogen has 5 valence electrons, and I'm actually just going to write 5 here. So 5 plus, how many does each hydrogen bring?
6.
Look at hydrogen. Where is it? What group is it? Sorry. It's in group 1. So there's 3 hydrogens. Each of them bring 1 valence electron. How many valence electrons are at the party now?
8.
Add. Thank you. 5 plus 3, 8 valence electrons. All right, so that's all we have to work with. And this is a reminder. The valence electrons are the only things that are mobile. They're the only things that can either be shared or donated. The inner core electrons, all of those stay put because they are stuck because they're underneath all the layers. So that's all we care about are valence electrons. Second step, choose central atom. So basically, this is the cool people that all the other atoms kind of talk to. So they just kind of surround that one. The way you choose the central atom is usually it's the unique one. Okay, it's the singleton. Maybe everybody's trying to get with that single nitrogen. Yeah. I can keep going? So there's nitrogen. It's the single one. It's the one in the middle. The hydrogens are going to bond to it. They're going to surround it and bond to it. So they bond by forming covalent bonds. And how do you draw a covalent bond? How do you draw it? Line. Okay. Line, line, line. And I'm just doing them so they're all spread out. You always want to create symmetry. So what we just did was we bonded these hydrogen atoms are called ligands. Okay, ligands are like legs, appendages. Okay, they're legs. Okay, so first step, count valence electrons. Second step, choose the unique central atom. Usually it's the singleton. Bond the ligands with 2 electrons, and I know that because that's what the line means, is 2 electrons. Right now, stop and tell me how many valence electrons we've used. 6, and we got 8 to work with, right? Okay, so now the fourth step is to add additional electrons to make octet. That just means every atom has to be satisfied with octet. The only exception, except hydrogen, because it's too small. So remember helium in our previous periodic table? I was like, oh, it's only got how many dots? 2 dots. Hydrogen is just as small as helium, or smaller, actually a little bit bigger. So it can only accommodate 2 electrons. So right now, hydrogen is happy as can be. This hydrogen here, so just make sure you're looking up here, so as I can't show you unless you're looking. Hydrogen here is surrounded by 2 electrons. It's surrounded because it's bound with 2 electrons. It's happy. Hydrogen here is the same, happy. Hydrogen here is the same, it's happy. Nitrogen has how many around it totally? But right here, right now, 2, 4, 6. Remember, you can double count them because they're just sharing. Sharing is caring. So the way you get octet is that you add a lone pair. Those 2 dots right there that I just drew are called a lone pair. Why does that make sense? They're all alone, and they're a pair of electrons. That's it. They're not shared with anybody. They're just nitrogens. So on the total molecule now, I've got 2, 4, 6, 8. I got octet. Okay, I've got octet around nitrogen, and then I go back and double check. I'm only allowed to have 8 electrons. Boom, I got 8 electrons. I'm happy. I didn't overuse, I didn't underuse. And that actually has a structural name, and we'll talk about that in a second. Yes?
Why doesn't hydrogen have 1 electron?
Why doesn't it? It actually donated its 1 electron to nitrogen so that it could share. Not donated, sorry. It shared its 1 electron with nitrogen. And nitrogen shared back, so it overall has 2 electrons shared with it, or between them. Okay, so that has a name. We're going to go back and name that. Let's do exactly the same process with name that for me. 1 second. Name that for me first. Carbon. Say it again. Tetrachloride. You're thinking prefixes because that's a covalent structure. Nominal, nominal. Question. The hydrogen is too small, so it's only going to get the duet rule. The duet just means 2 valence electrons surrounding it. And so add additional electrons to make octet. We did that. Okay. So I'm going to do this one in red for us. First step was what?
Count valence electrons.
Tell me. Count them up, people. How many does carbon deliver? You're looking at its group number. You're saying, okay, carbon has 4 valence electrons. There are 4 chlorines, each carrying 7, because it's in group 7. You're just looking at the group number. So what's 4 times 7?
28.
Plus 4?
32.
32 valence electrons. Wow. This one's going to be a little bit bigger. Okay? Second step. Choose the central atom. It's usually the singleton or the unique one. Carbon in this case, because we got 1 carbon and 4 chlorines. So carbon's in the middle. Next step. Draw your ligands, right? How many ligands am I going to draw? I have to count for every other atom here. 4, because I have 4 chlorines. Because I've already accounted for carbon. Now I need to get the 4 chlorines on the picture. And we got a north, a south, an east, and a west, okay? So we draw them spaced out symmetrically as possible. So there's chlorine, 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 chlorine. Okay, so we're going to add, how many valence electrons have we used thus far? 8. 2, 4, 6, 8. So who's already happy? Which one? Carbon. Carbon is the only one that has 8 electrons. Each chlorine is considered separately. That chlorine here, how many electrons does it have shared with it? Just 2. It's not happy until it's got 8. So how do I draw 8 on it? Lone pair, lone pair, lone pair. All right, so now chlorine here has 2, 4, 6, 8. It's good. Who do we appreciate? All the lone pairs are drawn on the chlorines around. I can wrap that, okay? Okay, so I literally went through and I just went ahead and gave everybody octet. I haven't counted a single one yet though. So right now I've got carbon with octet, chlorine with octet, 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 octet. Let's double check our counts and make sure we didn't go over or under our 32 valence electrons. I counted 8s, okay? So 8, 16, 24, 32. 32. Yes, so you always want to double check your counts. Okay, that's it. Yeah.
What happens if you go over?
If you go over, you have to erase and readjust. We'll do one of those. Not erase the whole thing, just erase like one thing and adjust. Yeah, you don't start from scratch again. It's too much work. Okay, let's do this one. Name this for me. Sulfur dioxide. You probably don't even have to look at your periodic table unless you don't know a symbol name, okay? Covalence, you don't crisscross. All right, step 1. This should be faster now. Step 1. Valence electrons equal, tell me the numbers. Sulfur has 6, group 6, plus 2 oxygens, which each have, again, 6, it's in group 6. Okay, so total? 18 valence electrons. Who is my central atom? Sulfur. Then do what? Ligands. So how many? 2. So let's put them on opposite sides because we want to make it symmetrical as possible. O and O. How many electrons have I used so far? 4. I've got a couple more to go. So here's the time where I'm going to add what? Lone pairs to give everybody octet. And I already know, I'm going to tell you up front, we're going to have to erase some of them, but work with me here. Process is this. Octet everybody up. So 2, 4, 6, 8. Oxygen's now got 8. Sulfur right now only has 4, so 2, 4.
So then 2 on top.
2 on top, 2 on bottom. And then this oxygen needs octet by adding what around it? Same, so 6 there. Alright, so right now I've got everybody with octet, everybody's happy. But is this a valid Lewis structure? Valid means it does not have over or under. If I go back and count, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have 20 on here. What do I need to do? Okay, what I need to do is I first need to take away 1 lone pair. I'm going to take away 1 on the oxygens on the right side, just right here. So I'm down to 18, but oxygen is not happy. What if I took away 1 from oxygen's lone pair, 1 of sulfur's lone pair? That brings me down to 16, correct?
Right.
But then I make them share 1. Sharing means middle, means add a line in the middle. So all I did was I took away 4 electrons and I added 2 back. So that got me from 20 down to 16 and I added 2 back to go 18. So if you have too many, you make them share another bond. So this one has a double bond and a single bond in it. So if you double check 2, 4, 6, 8, oxygen's happy because that's 2, 4, 6, 8 because those count doubly. And then sulfur's happy, 2, 4, 6, 8, and then the other option's happy, 2, 4, 6, 8. It's just they're sharing more. Okay, let's go now. I think we're getting the hang of this. You gonna do one more?
Yeah.
Okay. Let's do. I'm gonna wait on that one up there. Let's do nitrogen. This is diatomic nitrogen, and I haven't showed you the diatomics yet. This is called diatomic. Why does that make sense? 2 atoms. Okay, 2 atoms of nitrogen. First step. Electrons, count them up. 2 times 5, because that's the group number. Don't forget. Okay, so that's 10 valence electrons. Who's the middle? Nobody. It's just nitrogen bonded to, guess what? Another nitrogen, because there's only 2 atoms to consider here. Okay, how many electrons have I used so far? 2. So what do I need to do for everybody first? Give them octet, so 2, 4, 6, 8 on that nitrogen, and then you're like 2, 4, 6, 8 on that nitrogen. How many total dots do I have, or how many total electrons do I have on this image so far? 14, so I've got 4 too many. So what do you think I'm going to put in the middle?
Three bonds.
So a triple bond. So now we just did a single bond, we did a double bond. Now that you're 4 too many, that means you're going to have to erase 4 from there and there. Okay, but now neither nitrogen's happy. So I should make them share, right? So I'm like, all right, let me make them share. Recount my electrons. 2, 4, 6, 8, 10, 12. Oh no, I've still got 2 too many. So again, you go through that process of erase, erase, make them share. And sharing is always the golden rule, right? Sharing works in chemistry too. So then you double check. This side over here, this nitrogen has 2, 4, 6, 8. And this other nitrogen, which is sharing the same stuff, has 2, 4, 6, 8. It's surrounded, yeah.
So each line on a bond just means 2 electrons.
So if you have 3 lines, that's 6 electrons. There's 6. Okay, on the back of that electronegativity sheet, you see some little tables with some shapes, ligand counts, and lone pairs. So we're going to go back to image 1 we drew. Okay, so looking at nitrogen, every time you're looking, right now we're deciding on the shape. Because these molecules actually have shapes. That's what the first thing we talked about today with covalent stuff. They have shapes, and they have names to the shapes, so you can visualize them. So the very first thing you do is you look at the central atom, and you count the number of lone pairs. So, number of ligands. Nitrogen has how many ligands? How many legs on it? 3. 1, 2, 3. Because that's the attachments to other atoms. How many lone pairs? 1. What shape does that correlate with? Trigonal pyramidal? You guys can murder some names. Trigonal pyramidal. Okay. Basically, I wish I could stand on the desk. I'm not going to stand on the desk. Basically, what that looks like is if my head had a huge lone pair on it, and my 2 arms and my feet together were 3 ligands. Actually, I can put my butt up in there, but I'm not. So the lone pair pushes these arms and the legs down. Because what are all these things made of? What's the lone pair made of? Electrons. And what are the bonds made of? Electrons. And what do electrons do to each other? Repel. So my head is repelling my arms down and my legs down. So it makes me come up like a pyramid. I don't know if you can, you'll be able to see it with these little guys better. Okay, so basically, if a lone pair is here, it's huge. It's very, very, very negative. That negativity is pushing down on that bond, and that bond to make it appear like a pyramid. Can you see the pyramid? Kind of. It's just because it's repelling those ligands because they're also negatively charged. So trigonal pyramidal appears as the shape. And so that relates back to, I'll show you in a second why that relates back. Let's go ahead and do this shape. Carbon. Carbon has how many ligands? 4 ligands. How many lone pairs does carbon have? 0. What's the shape? Tetra. Why does tetrahedral? 4. Tetrahedral. Kind of like a tetrahedron. Tetrahedron has 4 faces. This is tetra, means 4 legs. Tetrahedral. Cool? Cool. Tell me sulfur dioxide shape based off the fact that it has how many ligands? 2. So 1 ligand on this side, 1 ligand on that side, and a single lone pair. So 1 lone pair, 2 ligands. Shape? Bent. That shape is bent. So that looks like this. Yes, water is also bent. You will get that chart 100% of the time, okay? You do not need to memorize those, but if you don't know how to use it, it's useless. It's just a piece of paper, right? That is what bent looks like. It's like this. Why does that work? Because this lone pair is doing what to that side and that side? Pushing them away. So normally, see how I drew it straight? I drew it straight because you need to think about what the electrons are doing to each other. My head being the lone pair does what to these bonds over here? Repels them. So it makes them appear bent. So I drew it this way, but really it looks like this. Looks like that. Okay, so that bent shape is important. There's something else I was going to tell you here. Oh, why does this come into play with that whole VSEPR theory? What does VSEPR mean again? valence, shell, electron, pair, repulsion, right? It's repelling. That's where the repulsion part comes in. Yeah? Yeah.
So why don't we say skeleton instead of shell?
Because this is what this verse stands for. That little mnemonic thing I made was just simply a way for you to help remember the steps of how it works. So count your valence electrons, make the skeleton, add electrons. Do you have to add pairs? I don't know. Review it to make sure. I made that up for you guys. So if this helps you remember the steps, that helps you remember the steps. That was just some silly stuff I make up, just for you. Okay, there are. How much left here? I do need to talk a bit more about some of our the more vocabulary part that goes with this. But I also want to give you this. I'm gonna let you guys start with this for a second. Maybe I'll do the first one with you. Okay. This is what we're going to be doing in our lab, not tomorrow, but Thursday and Friday. And I want to make sure that you're good with this by starting on the new class. And this part is going to be something that we're going to do in pieces. So you are not expected to do this whole part tonight. You're not even expected to really get started tonight, except for maybe like half the structures. There's not a whole lot you can do. I think I passed back surplus to make sure everybody gets one. So I just passed back a table. The table has like 12 structures on it. 12 structures. Oh, I gotta do one of these charts ones for you in a second. I have so many. Just okay. So what's the first structure on your sheet? First guy. CH3Cl. Okay, you do not know the name of this structure. Okay, that's totally fine. We're not going to learn that much. First thing you do on column 1 is to do the bond polarity. Bond polarity just means, actually we'll do that in a second. Let's do the electron dot structure. You see that's the next column? Electron dot structure. And that's a really small box. Sorry. If you want to write this on a spreadsheet paper, I just realized that's so small. Alright, so the very first step for this is V. What's V mean? Valence electrons. How many valence electrons does each of these carry? So this is part of your homework. Do this with me, okay? How many does carbon carry? What group is carbon in? 4. What group is each hydrogen, or what number of electrons is hydrogen carrying? So I'm just saying 3 times 1. 3 times 1. You guys with me? Okay. Plus chlorine. 7 valence electrons. You're only looking at group numbers. Add that up. 14 valence electrons. Okay, so that's our total. Next step. Find the singleton one, right? Now, if carbon is in it, carbon wins. Carbon loves bonding with other people, okay? Put it in the middle, make it happy. Carbon wins. And this one, I know we've got carbon and chlorine to choose from. Carbon always wins. That's another unwritten rule. Okay, so carbon's in the middle. What do you do now?
Ligands.
Ligands. So what am I drawing? What's going up? Give me one of them. Cl? Okay, cool. What's going out here? H, H, H. Stop and review. How many electrons have you used thus far? 8. I've used 8 so far. It's 2, 4, 6, 8. Okay? Now, who is unhappy? Meaning not octet. Well, some people are okay with not having octet. So chlorine's not happy. Why is hydrogen okay? It's little and it can only accommodate 2 electrons. So that's 2, 2, 2. So all the hydrogens are good. So chlorine needs some extras. Count up. So I've got 2, 4, 6, 8. Chlorine is good. Carbon's good. 2, 4, 6, 8. That's good. That's 14. Is everybody good? Okay, so all atoms are good. We've got 14. We're good here. That's the Lewis dot structure. Now the bond polarity part's just a little different. I needed to do the Lewis dot structure so I could see who was bound to who. So carbon is bound to chlorine. Yes? Flip over your electronegativity sheet and tell me what the numbers for carbon and chlorine are.
Carbon is 2.5.
And chlorine is 3.1. Difference? 0.6. What field is that? Polar or non-polar covalent?
Polar.
Polar covalent. You see that we just looked on there, found the differences, and we said it's polar covalent. What do you absolutely have to drop as polar covalent? The arrow. Dipole moment It's got a name, but call it arrow, I get it. Where does the arrow point?
To the right.
To the right, towards chlorine. So now that we know this, we actually can draw that on our structure. And that's very, very important for tomorrow, okay? So, or Thursday when we do molecular polarity. So I'm just going to draw this little arrow from from carbon to chlorine, just to point it up to indicate that up here, it's kind of got like a negative field around it. Got a negative, partial negative charge. So that's kind of got like a partial negative up there. And you don't have to write that, but just draw the arrow point, and that's good. Now, there's another bond here. What? Carbon to hydrogen. Carbon's got a 2.5. Hydrogen has a
2.2.
2.2. That difference?
0.3.
0.3. Polar covalent or non-polar covalent? Non-polar covalent. So if you just write, draw me the little bond, and then you can do the numbers out and just say non-polar covalent and polar covalent in that little tiny box, then that works. You're probably won't fit that much, but at least you know the process, so you can do that by yourself. Otherwise, though, non-polar covalents, I don't have to draw a darn thing. That structure is happy as can be. It's good. Yes, ma'am. Yep. Don't draw anything. Only if it's polar covalent, you have to draw the unequal distribution of electrons.
Does it matter what order you put them in?
Nope. Does not matter what order, because it's a 3D structure. So it looks like. I just took a bond. It looks like this. So that chlorine could be the purple one. It looks like that. So it doesn't really have a location. It's just there. Okay, next one is best for shape. So tell me the shape of this one based on your back of your chart. So tell me the steps though. You look at carbon, it has 4 ligands. How many lone pairs does carbon have? 0, so the shape is tetrahedral. Okay, and then I don't think you can do anything else. Nope, the rest of that stuff we're learning another day. All right, so by Thursday, you have to have the first 3 columns filled out for all of these. Start them tonight, okay? And then I think you guys are getting it. I don't know that I want to do these notes here, because this is what we talked about. You can read that. You can read it, and I think it should make sense. But I think when you start fiddling with the little Lego structures, that it'll make more sense. You can see the stuff pushing and pulling and stuff like that. Leave the yellow sheets stay here because that's for my next class. But you guys have 4 minutes left in class. Maybe get one more structure drawn, okay? Since you're sitting here, big chillin', not big chillin', but working. Draw another structure with the person next to you. Yeah. The next one is what kind of compound right now? What kind is the next one?
What did you say?
It's ionic. So how do you draw ionic? With the whole like, hey, here's my electron, you can have it. That's the only one that's ionic that's on there. Okay? You might want to go ahead and note that that's ionic. That's not the normal one. The second one is ionic. How do you know it's ionic? Never went on at all. I'm here after school for tutoring if you need me. And thank you for sending your videos. If you still haven't sent videos, it's fine. We'll get them soon. We'll get them soon. Oh, I gotta email Teal. Oh. Huh? Oh, my next
Yeah. Well, I think when I was going, my to the test, I think I missed the words to forage.
It's on the website. It tells you exactly what's wrong. Yes. Hey guys, the server was down last night. I had two people ask me about test grade servers. I don't know if you guys heard of that. Canvas wasn't working, server was down, PowerSchool wasn't working. So I'll put your guys' test grades in, and after I get one last person to take the test,
I'll give it back to you.
So, I know that I need. Oh, there's a couple of things.
Bye, guys. I'm cooking so much.
You're what?
I'm so hungry.
Uh-oh, Kendall left his keys. Miss Angela. Okay. Miss Angela, this was for Kendall's desk.
Disney, nice.
Oh, it might not be his, but for the quiz tomorrow, we just have to review, because it's